So I can also show you charges on conductors with this interesting device. It's a bell where if I bring a charged rod nearby, it rings. And I take the rod away and it stops. And I bring the rod nearby and it rings. And take the rod away and it stops. So let's think about how this thing is working and what's going on. First of all, it's called Franklin's bell. After Benjamin Franklin, who invented it and popularized it, although there's some debate, it may have been invented by Andrew Gordon, who I think was a hockey player, so that's a little bit unusual. But basically, it's a bell, and all the parts I'm drawing here are metals. They're all metallic conductors. So there's this bell, and it is connected to ground. So it's connected through a conducting rod. It's the middle bell here, right there. It's this bell right here. This whole rod is a conductor, and there's this wire is going to ground. So in terms of electrostatics, this thing has an infinite well of charge that it can give to the bell. The bell next door is over here, and it is connected as a metal, as a conductor, to the rod that goes across the top. Okay? So it's a big conductor all the way across the rod down to the bell. This big rod is here because there's supposed to be two bells, but I'm trying to make it simpler, so I took it apart a little bit. Okay? And then hanging in between is the little clanger ball. It's also a metal, sitting right there. It's hanging by an insulating string. And that's the whole setup. Okay? So let's think then about what happens. So neutral metal, grounded neutral metal. All that's happening. What we do is we bring in the charged rod. So here, we'll say in cross section, I guess, there we go. The charged rod comes in. The rod is very negative because it's Teflon that was rubbed with cat fur. What that does is that pushes the electrons away, and they end up in the bell. And it leaves this part of the rod positive. Okay? The exact charge distributions are very complicated with field lines and complex surfaces and chains and all that stuff. So I'm not giving you exactly where every charge goes. But basically, this negative charge is going to push negative charge into the bell. Okay. The ball is sitting here. A little conducting ball is the clanger sitting there. This is neutral, doing nothing. But the ball sees a negative bell nearby covered with negative charge. So this negative charge pushes the negative mobile charge in this conductor over here, okay, which leaves this side positive. Fine, but we just talked about the fact that this ball would feel a force this way. So a little conductor is always attracted to charge, even if that charge is in another conductor. Instead of an insulator, now we have it induced charge in a conductor. But since this positive is closer and this negative is further, this feels a force that way. Okay? And it feels a force, it's free to move by this loose string, so it's going to fly up there and hit the bell. So we can erase it real quick and draw it again and say now it goes up here, and there's your first ding. It hits the bell, makes a dinging sound. Now let's see, it did have positive here and negative here, but when it touches, what happens? Some of this negative says, oh, I'll cover up those positives. Okay, so it takes those out, and now you have a negatively charged ball. Now it's basically a continuous conductor with this bell, but it's a piece that can fly off. So these negatives are now repelled by these negatives, so it feels a force back that way. Electrostatically pushing, and also just gravity, it's probably mostly gravity, is now pulling it down, now that there's no force pulling it back this way. So it falls this way. And it goes through zero, and it's negatively charged. It has momentum, it keeps going. So it comes over here, got its negative charge, hits this bell, and there's another ding. This thing is grounded. It'll happily take these electrons away. You're too charged up, you want to get rid of your electrons, they'll go here. Now we have a neutral ball. There's no reason for it to stay here. Gravity pulls it back down. And the process now repeats. Now we're back to a neutral ball in the middle. So what this thing is doing is under the forces of a conductor near charge, it's moving up, it's picking up negative charge here, it's falling and it's delivering it here. And on each cycle, it rams into the bells and it makes a sound. When we take the rod away, everything becomes neutral again. It has no reason to keep going. Sometimes it kind of keeps shaking a little bit, but nothing really drives it anymore. So let's look at that again and see if that makes any sense. See if it'll still behave. Let's see, so we bring in our rod, and there it goes. Ringing, pull the rod away, and there it goes, finally stops. Let me charge it up again. And another thing I can do is I can make it go, but remember, I'm a big conductor, so if I touch it, that kills the ringing, because I just took all the charge away. This part has to be charged up for it to ring. If I touch it, I take the charge away, because I'm basically the same as grounding it. See, went away. Try that one more time. And I make it ring like that, touch it, and then go away. Wait a minute. It didn't stop that time. Hold on, let's see here. Something strange. It's supposed to stop after I touch it, right? So we can make it ring, touch it. And then it stops. Okay, that was fine. Make sure, I don't want to leave any mysteries of physics. The goal of this class was not to destroy classical physics. Maybe what happens. So I make it ring, touch it, and then walk away. So it's speeding up sometimes after I touch it. I know what's happening, and I'm going to leave it as a mystery for the forums. See if you guys can figure it out. Why was it sometimes when I touch it and walk away it stops, sometimes I touch it and walk away it keeps going?